Now I want to talk about concavity of log. So Logisim inequality. So here we consider non-negative numbers a1 through an, b1 through bn. And this part is sum of numbers. And this part here is summation of numbers times log of sum of numbers over sum of numbers. So log of ratio, at the top we have a sum of numbers according to A's, and the sum of B's. Sum of A's, sum of B's. And this one holds with the equality if and only if AI over BI is constant for all I. So this part is sum of numbers. This is a sum of numbers, but here is a single number, basically. Log of ratio and the sum of numbers. So I said that these are sum of numbers. Basically, both are numbers. A single number came out to be. Now, if we want to prove this, obviously we have to use Jensen's inequality, and then we need to come up with a function. Okay, so sum of numbers. So it's supposed to be expectation of numbers or average of a function. Here, function of average. Okay, so it is a single number. So average of a function is greater than function of average. So what is this case? Where should the inequality goes? So this is, I think this one is convex case, right? So this is function of average. This is average of function, right? So average of function is higher. So this is average of function. This is function of average. So we need to come up with a convex function to show this inequality is true. And then we came up with this function. Basically, this function is a product of log t, which is this one, and we have t, which is from 0. So the slope is 1. And then we are taking the product. So at the origin, it should be equal to 0. But when it is far away from 0, it should follow the log function. So there is a compromise between these 2 points. And when it is equal to, when these 2 are multiplied, it is 0 right here, so it should go this way. So that should go this way, okay? So that is this function right here. And then when you have done this, if you take the derivative twice, it is 1 over t. So for non-negative t's, that is a number, I mean, second derivative is positive all the time. So it is a strictly convex function. Okay, for strictly convex function, we can show that you can use the Jensen's inequality. Average of maps, average of functions is greater than or equal to map of average, and that is the case. And then based on this, we come up with this one. Alpha should be here, distribution, right? Because it has to be average of function, right? And then the function of average. So alpha i's are a number between 0 and 1, and then some of them should be equal to 1. And the ti is non-negative. Okay, so ti is a positive, sorry. Then we let alpha equal to bi over sum of bi's, and ti is equal to ai over bi. Then substitute this into this expression right here, then we will get this. Okay, you can do that, right? And then equality is obtained if and only if these ratios are constant for all I, as we have seen in previous case. So log sum inequality has been proved. So that's the sum of numbers, sum of logs, average of logs, and then product of numbers. That is the expression. And then inequality goes to the left-hand side. So we have to remember that. And let's move on. So we may use log sum inequalities to show relative entropy is non-negative. So this is the expression that we have. So as you have seen, the sum of logs, and this is number, because the sum of px, and the log of sum of px over sum of qx. So that is the right-hand side of log sum inequality. And this part here is 1, that part here is 1, this part is 1, 1 over 1 is 1, so log of 1 is 0. So this is 0. So log sum inequality can be used to show that relative entropy is non-negative. And we can also show that relative entropy between P and Q is convex in the pair P and Q. So this can be obtained using log sum inequality, and it is shown right here. Okay, so in this case, I said this function of P and Q, in order to calculate relative entropy, you need to give P and Q as an input. So this relative entropy is a function of argument P and Q. All right. So we can talk about the convexity of relative entropy based on P and Q together. Okay. So P and Q as an input, right? So you can think of it as a vector input. Okay. So D P and Q is convex in the pair P and Q. So you have to consider this convexity over the pair. Okay, so mixing distributions decreases the relative entropy. Basically, if we talk about this, if we mix the two pair, and that will give you a smaller relative entropy. So let's consider that. So consider two pairs, let's say P1, Q1, P2, Q2 of distribution. So these are the distributions pair, okay? Pair of distributions. Which one is bigger? So basically average of relative entropies of these guys, or relative entropy of average distribution. So average distribution here means average of P1 and P2, average of Q1 and Q2. So that is this, nothing but. So average of function, right? And then here, function of average. Okay? And then one supposed to be bigger than the second one, according to Logisim inequality. So the first part we consider. So P1, this one is P1 log P1 over Q1. Okay, that is this one. Plus P2 times log P2 over Q2. So that is the second part. Okay, now we consider relative distance, relative entropy between that distribution and this one, which is average of P1, and then log of average of P1 over average of Q's. So log of P's, I mean the average of P's, and then log of average of P's over average of Q's. So as you have seen in the Logisim inequality, the first part should be greater than or equal to the second part. As you have seen in Logisim inequality, this takes the role of the average of numbers, right? And this is a product of numbers, right? So that's greater than the second part, okay, due to Logisim inequality. But that is not equal to 1. This is 1 prime. So how do you make it, make 1 prime equal to 1? The only thing that you have to do is take summation over x on both sides. So on 1 prime, if you take the summation over all x, it becomes 1. If you take the summation on x on x 2 prime, then you get 2. So the proof is completed. Now I want to talk about concavity of entropy. We call the proof that entropy is maximum when the distribution is uniform. Let Ux be uniform on X, then we call this was the proof that the entropy is maximum when the distribution is uniform. And we want to show that not only the entropy is maximum for uniform distribution, but it is also a concave function of Px. It is a concave function of Px. That's what we want to show. If it is a concave function, that means hold on. Then entropy function looks something like this. Then you can do optimization. For example, gradient search, or if you take the direction of increasing entropy in each iteration, then you can come up with a numerical optimization procedure to find the best distribution or best way to come up with the distribution that achieves the maximum entropy for a particular example, particular random variable. Okay, so the concavity of entropy is proved basically because this distribution, we said that it is a convex function of P and U in previous page. So minus relative entropy is a convex function of P and U. Thus, H of P given U fixed is a concave function of P.